This is a demo of our new Interactive HorizonCube auto tracker. The workflow is developed in the context of the OpendTect SIS Consortium, a joint industry project that aims to improve the HorizonCube technology and its applications. The workflow that will be demoed is developed for 2D seismic. It will be released as part of the HorizonCube plugin in OpendTect version 5.0 that will be released officially at the SEG conference in October. This interactive 2D workflow is the basis for all future 2D and 3D horizon trackers in OpendTect. It will be extended from 2D to 3D inside the SIS Consortium, and the same interaction will be implemented in the next generation amplitude and similarity auto trackers that are under development as well. It is our goal to build the best set of tools available in the market for tracking horizons, be it 2D, 3D, single horizons, or a dense set as in HorizonCubes. The workflows we develop give full control to the interpreter. The tracker operates in regions that progress from multiple seed positions. In this demo we will be using a random line extracted from 3D seismic data located in the Australian Northwest Shelf. We will apply the new workflow on a Triassic reservoir interval that is faulted mostly due to extensional tectonics. The workflow consists of 3 steps. First, we will create framework horizons using a dipsteered auto tracker. This is the same tracker that will later on create a HorizonCube. For this we need a 2D dip steering cube, which in this demo is already pre-processed. In the second step, we create 2D HorizonCubes. These are computed per region. A region is a closed area bounded by faults and framework horizons. In the third and final step, we interactively correlate the HorizonCube events per region to produce a correlated final HorizonCube. We first launch the HorizonCube creator. Now we press the Create button to create our new HorizonCube. I will keep this window open and I will close the control center. Ideally, you would have 2 screens for this. Here we select the line and the pre-processed 2D steering cube. As the interval is faulted, we either pick or load fault sticks. In this case, we load them. We want all horizons to stop against the faults. Hence, we set the boundary type to forbid cross. We press OK and the faults are loaded and added to the tree and scene. We can now choose whether we want to display the already existing horizons or whether we want to pick our own framework horizons. If we use the existing horizons, the interpretation is already prepared. You can use that as an existing framework and proceed to create a HorizonCube. If you do not want to use them, you can always throw them out and add your own horizon. We will pick our own framework horizons. First, we will position our mouse on the event where we want to pick. One click will create a horizon from that seed. The seed is by default available under this button. Here you can see the interpretation already existing. If you are unhappy with the interpretation, you can click in any given fault block to pick multiple seed locations. This will automatically create a horizon using steering. If you are unhappy with a seed position, just press Ctrl, click to remove it. We will now continue to pick our framework horizon. If you want to pan, you can always escape by pressing this button to see the rest of the seismic section. If you escape back, it will return to the picking mode. We have now finished our first horizon. We will now add the next horizon by pressing the plus button. Now we can interpret the lower boundary. For each fault block I am inserting a seed to extend that horizon. Now that we have prepared the framework, we proceed to create a HorizonCube by pressing this button in the same window. Keeping this window open is important. It allows you to add more framework horizons, and the HorizonCube results will be interactively updated. We will create a data-driven HorizonCube. Please notice that in the setting window, the set of regions is presented in the form of a table. A region is defined by 2 input horizons and adjoining faults. The regions are defined per package. you can activate a region by hovering over it with your mouse. You can see that it lights up, in this case in the color green. Further note that you also see a vertical line in the display that is placed at the center of a region. This is the seed position of the HorizonCube. It is a very important parameter that can be changed manually. A seed position should always be placed in a good data quality area and in the thicker portion of a region. We try to avoid seed positions near faults, as the data is often more noisy. In the settings window, you can change the color scheme to your liking. You can also choose to skip a region, for example, when you are crossing a chimney or a salt diapier. Let's accept the settings and process the HorizonCube. As soon as the job is finished, a wheeler scene is launched. The wheeler scene is a flattened scene in which all events of the HorizonCube are horizontal. The y-axis in the wheeler scene represents relative geologic time. We display the same line in the wheeler scene to check whether all seismic events are indeed flattened. If this is not the case, we can add more framework horizons and update the HorizonCube with more packages. As you can see, this event is not flat, so we are going to pick this event in the wheeler scene. We are going to add a horizon and start the interpretation. You can see that wherever I am picking a horizon, it is transferred back to the normal scene. This is the horizon that has been interpreted in here. You have an option to continue back to the normal scene, or you can stay in the wheeler scene and continue picking. We are going back to the wheeler scene. We have updated the HorizonCubes by pressing on the HorizonCube icon. Now we can see everything is flat and the wheeler diagram is aligned. As the HorizonCube is processed per region, we need to correlate events over all regions to create a final product. We press this icon, which is specifically designed to correlate multiple regions. There are 5 sliders controlling a batch of 5 regions. In case there are more than 5 faults, the batch of sliders is moved along the line. We will correlate this prominent seismic event from one region to the next using the sliders. When you are happy with the correlation, you can run it. Once the correlation is performed, we will have a merged HorizonCube with an equal number of horizons everywhere. This is our final product. For more information, or to request a demo license, please visit our website at www.tgbes.com. Thank you for your attention.